So it's a pleasure being here today, and I will tell you about studies of the ferroelectric phase transition with the deep potential model. In fact, this work has been supported by the Department of Energy that supports a center that we have in Princeton that is called Chemistry in Solution and Interfaces. There is nothing to do between with the chemistry in solution and interfaces in this talk, but at the chemistry and solution and interfaces, we developed the deep potential model and these methodologies that allow to boost ab-initio molecular dynamics and the ferroelectric phase transition was an ideal system to study because in this model we can represent not only how the potential energy surface depend on the atomic coordinates, but also how the polarization, the dielectric polarization, depend on the atomic coordinates, which is what is called the polarization surface. So let me move on. Now, the ferroelectric phase transition can be described within mean field theory as a rather simple example of broken symmetry of an order parameter, which in this case is the polarization. In the high temperature paraelectric phase, the system is the potential, the free energy as a function of the order parameter shows a minimum at the symmetric structure, but by lowering the temperature, the system develops an instability, and there is a structural transformation from cubic to a lower symmetry phase in which a dipolar moment arise, and this description, this instability has long been thought to be due to a soft mode instability of the lattice that will amount for there should be a frequency of a phonon mode that goes to zero as the temperature approaches the critical temperature, and similarly the inverse susceptibility should go to zero again as in the Curie-Weiss law. There is also another mechanism that can explain this transition, and which is these two mechanisms are not mutually exclusive, so there can be some of this effect and some of this effect. In this case, in the order disorder, the spontaneous polarization results from establishment of long-range order, like in an Ising model. Now, the question is, how do fluctuations modify this picture? And can we learn something about that from molecular dynamics simulation? That is the subject of my talk today. And let me discuss some other background material. So typically this phase transition has been studied with atomistic model based on density functional theory. David Vanderbilt and Karin Rabe at Rutgers have been pioneer in this effort, and they developed effective Hamiltonians that are parameterized on the base of density functional theory calculations, and which in this effective Hamiltonian there is a reduced number of degrees of freedom. There are also models in which all the atoms are the degrees of freedom, and these are based on empirical force field that are based again on few meaningful physical parameters that are fitted to DFT calculation and perhaps also to experiment. Recently, all atom force fields that reproduce accurately the density functional theory have become available. In this model use artificial intelligence techniques, namely machine learning, to define the parameters of this model. There are many parameters in this model, and these parameters specify a deep neural network representation. So this model reproduces accurately DFT, and the deep potential methodology is just a realization of this approach. Let me just explain briefly what that is. Essentially, this is a coarse grain of the DFT calculation from which we extract the potential energy surface, so the dependence of the potential energy on the atomic coordinates, and this free energy surface is represented by a sum of atomic energy. This index I runs over all the atoms, and each atomic energy is given by a deep neural network that depend on the coordinates of the atom in the environment of the atom I. So it is a sort of generalized embedded atom model. But the dependence on the atom include many atoms in the environment, and so it can be rather accurate. And in addition to that, we can also represent the polarization surface. So what is the dependence of this quantity P, which is a vector quantity, this is a scalar quantity, on the atomic coordinates. This is V is the volume of the sample, and using a maximally localized wave function, local decomposition of the cone-sham orbitals in DFT, this can be written as a sum of dipolar contribution coming from the ions or the nuclei, but here we use typically pseudo-potential, so we have frozen core electrons and pseudo-ion, and a contribution coming from the Vanier functions. And there is a constant here in this representation that is called the polarization quantum, and depend on the periodicity of the lattice. But since we are interested in application in changes of the polarization, this constant is immaterial, and because typically also the kind of changes that we have are smaller than the quantum of polarization that derives from the periodicity of the supercell that we consider in the system. So in this case, the position of this Vanier center, here we consider a spin saturated system, so there are a charge of 2 associated with each one of these Vanier center, is given by a deep neural network representation similar to this one, but this is a vector representation, this is a scalar representation. Since we have this local decomposition in a crystalline material, we can also associate this local dipole to the cell to the individual cell of the system. So we have local dipoles, and that we will see those are important for physical interpretation, even though the global order parameter is the global polarization that is given here. Now, with this approach, since we know the polarization dependence on the atomic coordinates, we can also easily include in the simulation the effect of a weak applied external field that can be static or dynamics according to this formula. And if the field is weak enough that linear response theory is valid, the polarization that we obtain in absence of the field will be good enough for our study. So this the coordinates essentially, this is independent in the sense that has been calculated for a subset of the atomic coordinate of the atomic configuration that are used to learn phi. We also compute maximally localized Vanier function, and we know the position of this maximally localized Vanier function. In fact, in systems like the one that I'm describing here, these maximally localized Vanier functions are always associated uniquely to a certain atom. So these are just the displacement of the center with respect to the atom, and the displacement of the center with respect to the atom is learned from the maximally localized Vanier representation. So we have two neural networks, and with this neural network, we can generate molecular dynamics trajectories, but since we know for each, since we know for each position of the ions or of the nuclei, we know where the Vanier centers are, we also can calculate that each configuration generated by molecular dynamics, we can generate this script P, or the change with of polarization with respect to a reference configuration that typically in those systems is assumed to be the symmetric configuration in which the polarization is zero. Does that answer? Yeah. What? Just one more thing. The parameters that define this network are independent from the parameter that define this other network. So this f here and this f here are not the same function. They are different functions that are learned again from the DFT calculations and allow us to know what the polarization is at each configuration generated by molecular dynamics. So with that, I want to present three case studies using this approach of system that are in which there is a ferroelectric phase transition, or maybe attempt of a ferroelectric phase transition like in PMN. So in this, this is a standard perovskite ferroelectric system, and the work was done by Ping-Chen Chi, Yi Shao, and also Wen and was involved. Then I will describe KDP, the KDP, where the work was done by Binja and also Ping-Chen, and finally PMN, where the work was done by Kehan, Kai, and Pinchen. So Pinchen is the driving force. There are three theses work partially describe the stuff that I'm describing today. These are the theses of Pinchen, the thesis of Binja, and the thesis of Kehan. And but as I said, Pinchen has been the driving force behind the ferroelectric application of this methodology. Let me start with PTO. PTO is a prototypical ferroelectric perovskite. This is a cell, a perovskite unit cell, and in which also the Vanier center are represented. And basically, we can study, for instance, how the ratio in this PTO, there is just one single ferroelectric phase transition at a temperature with a critical temperature of about 760 Kelvin in experiment. And this phase transition is a first order phase transition. And the system is on average cubic in the symmetric phase, in the high temperature phase, but it has a tetragonal distortion in the ferroelectric phase. Now, if we do just, we use one DFT functional here. We didn't study dependence on other functional, but I think that all the functional have limitation. And so the limitation, so we use scan here, but the limitation here is that if we just don't do anything, this is what we get for the C over A, and this is what happens in experiment. So the phase transition is predicted to occur with this model at a few hundred Kelvin above. This is a result of what is called the tetragonality error of the DFT approximation that overestimate the strength. In the tetragonal phase, there are chemical bonds that form, that compete with the ionic forces, and DFT overestimate the strength of the bond, and so overestimate the tetragonality. And it was already suggested many years ago by David Vanderbilt that a way to correct for this tetragonality error of hyper tetragonality or something like that, by applying an external hydrostatic pressure to the system. So in fact, we apply an external hydrostatic pressure of 28 kilobar, and we fix the value of 28 kilobar by fixing the C over A ratio at 300 Kelvin with the value that is observed in experiment. So with this empirical fix, the phase transition occurred much closer to experiment, and then we can study a number of properties. This is the deviation, and we can study also how the properties depend on finite size effect. In fact, we find that finite size effect becomes rather small only when we go to L equal 15, which means 15 by 15 by 15 unit perovskite cells. So we need to go to a rather large number of atoms. To a rather large number of atoms in order to reduce finite size effect. Now, this is the experimental result for the deviation of the enthalpy from the Dulong-Petit law, which is obeyed at high temperature in the paraelectric phase. And this is what happens in the simulation. We see that we have a behavior that reproduces quite well, at least qualitatively, the experimental behavior. This is also the value of the polarization, the order parameter for the simulation. And the values that we have here, there are in experiment, there are some large uncertainties due to the fact that there are defects in the experimental sample, but the value that we get is consistent, is within the range of the experimental values. And we can see here how the lattice constant, and this is also, we can compute the heat capacity, and this is the experimental heat capacity in two experimental samples that have been grown by float zone and by solid state reaction techniques. And we can see that we have, again, we have an even sharper behavior of the heat capacity. This is calculated from the fluctuation of the polarization in the molecular dynamics simulation. And we think that our sharper behavior is due to the fact that we have a pure sample. And we can also look at the susceptibility, again, calculating now. So this is the, this is the fluctuation of the enthalpy, and this is the fluctuation of the polarization. We get the susceptibility. This is the susceptibility that we get, and these are results from experiment going up and down. You see in experiment, there is the phase transition actually should occur over here, but there is a shoulder and the peak is moved to higher temperature that is supposed to do to strain field that are present in the experimental sample. And again, we can fit with the Curie-Weiss law the behavior above the transition, and this is the fitting with the Curie-Weiss law. Again, the value that we get for the constant is in the experimental range. So now, yes. These are just deep potential MD calculation. We can do, this is, I don't know, well, 15 to the cube for the cell is of the order of 20,000 or 28,000 atoms, something like that, and can be done easily with the deep potential model. It cannot be done with direct ab-initio MD. In fact, we tried long ago, but at most we could do a 3 by 3 by 3, and with a 3 by 3 by 3, the finite size are so large that you get only a hint of what may be going on, but not all these detailed results that we get here.
Right, and the reason you comment on the scan function is because
yeah, this was based, the DFT was based by scan, but I think we should get similar result if we did PBE or some other. I mean, there is no functional that is perfect, that for sure. And but unfortunately, in this kind of studies, still, in order to learn the coarse grain representation, you need a sufficiently large number of configurations that you can easily calculate with DFT, but with more accurate method is another matter. So that's if more accurate method can be used to learn this thing, we will have an even more accurate representation, I think. Now, this is at this point, this is just classical. This is classical MD. We generate configuration. So there is a classical kinetic energy associated with the atoms. And in the training configuration, there are T=0 configuration, but also finite temperature configuration that are extracted from molecular dynamics trajectory on a smaller system like the 3x3x3 that I mentioned there. But these parameters that describe the potential and the deep Vanier, I mean, the description, a local description is good. And so we can extrapolate with the local description that we have learned on a smaller model, we can extrapolate to a larger system size, and that is what we get over here.
Of these calculations, I need to know the change of the vibration frequency.
Well, this guy will discuss also that. In these calculations include full anharmonicity within the model. So when we go to this high temperature of the simulation, 800 or larger than 800, the harmonic description is not good enough. So that I will comment. But I mean, the advantage of molecular dynamics is that once you have a potential energy surface, you can include fully the effect of anharmonicity. And that is what these simulation do. So when we compute this, Newton's equation, we are solving Newton's equation of motion. Exactly. So now let me go on here. Now, can we learn something from the simulation about the microscopic mechanism of the transition? I want to say that PTO was long considered until 20 or 30 years ago, was considered a prototypical soft mode ferroelectric system. And the reason for that comes from these data here. This is the omega square of the mode above the transition experiment. These are different experimental results, whereas this black is the result with our molecular dynamics simulation, but I will comment on that later. So you see there is in experiment, there is a very good, this experiment done with Raman scattering, there is very good linear behavior of this quantity. On the other hand, when we are below the transition temperature, there is a linear behavior only quite well below the transition temperature, but when the transition temperature is approached, there is a strong deviation that is typically called the waterfall in this field, and they attribute that to a crossover between soft mode and order-disorder transition. So before going into how we can explain that, let me say a few words here. Since we have the cell dipole, we can plot the distribution of the dipole, of the absolute value of the dipole, as we go from low temperature to high temperature. And here there is, you see, there is a jump, but a small jump that corresponds to the transition temperature. And this is shown here. And so in the paraelectric phase, the local moment is not zero, but is different from zero. And we can learn even more if we look at the dipole-dipole, cell-dipole correlation function. There is long-range order up to the temperature of the transition that is at 821 with this model, and then there is a jump and loss of long-range order as we go in the paraphase. Similar here, this is the lead-lead pair correlation function. We can see that the displacement of the lead atoms with respect to room temperature doesn't change significantly around the phase transition, again, consistent with an order disorder, character of the transition. Now, I would like to say that again, the fact that there is significant order disorder character was discovered about 30 or so years ago by diffraction experiment, both X-ray and neutron diffraction experiment, in which they found that the position of the atom are distorted also in the symmetric phase. So locally in the symmetric phase, the average position of the atom is still distorted with respect to the perfect cubic phase. So this is consistent with those results. And now, can we understand this behavior in the optical spectra? Well, we didn't compute the Raman spectra. The Raman spectra will involve studying the autocorrelation of the polarizability, which we can do, and we have done in some cases, but not here. And here we look only at the infrared spectra that is related to this time autocorrelation function. And these are the result at below the phase transition and the result above the phase transition. You can see as the temperature, lower temperature, and as the temperature is raised, all these frequency, by the way, these are the frequency of this mode obtained from Raman experiment. So these modes are both Raman and infrared active, and they are actually captured quite well by the simulation. And we can see that above the transition, there is a mode that seems to be not broadened as the transition temperature is approached. And indeed, if we plot it here, we get an approximately linear behavior of omega square in agreement with the experimental data. And if we plot the behavior of the low frequency mode over here, we get, I don't remember which one is the, well, the molecular dynamics is the black. So we get something that reproduces the waterfall. Now, we were for a while wondering why there seemed to be a sharp or relatively sharp mode, but the relatively sharp mode in this calculation is masked by the fact that here we have the time derivative of the polarization, time derivatives of the polarization correlation function. If we compute the polarization autocorrelation function, there will be a factor of omega squared that comes in. And this omega square factor will actually eliminate what happens around the zero frequency. If we consider the behavior of the polarization, we see that the behavior of the polarization is actually dominated by a Debye relaxation mode at omega equals 0, which is what one expects for order disorder. I think that the same thing should happen in Raman, because in Raman, typically, when you go to frequency close to 0, there is the Rayleigh scattering mode that masks the effect of the Raman. And so typically what happens close to omega going to 0 is taken out by something that plays a similar role to the omega square the omega square place here. So we can understand this kind of detail based on those simulations. Now let me move to the second example. The second example is a system that has been studied for a long time, since the early work of Slater in the 1940s. And it is the potassium dihydrogen phosphate, KDP. And this is a typical hydrogen bonded ferroelectric. And in this system, the ferroelectric phase transition is first order. Structure changes from tetragonal to orthorhombic. And the system is characterized by a very large isotope effect in the properties. Namely, in KDP, the transition temperature is 123 and more than 100 K higher in the KDP at room pressure, at standard pressure in experiment. Also, I want to notice that the change of entropy, the excess entropy at the transition is about 30% more smaller in KDP than in DKDP, and that the polarization, the saturated polarization, is about 25% smaller in KDP than in DKDP. Now, isotope effect on static equilibrium properties are a manifestation of nuclear quantum effect. And so what is the microscopic picture? Now, in order to let me mention here early theories and experiment. Classical order disorder model was introduced by Slater that associated the polarization of the phosphate groups to the hydrogen bond. So one has this, in order of increasing energy, one has these ferro units that gives a dipole moment in the direction of the polarization, in the Z direction. And then there are Slater units that still satisfy Ice rule, but do not contribute a dipole moment in the polarization direction. And then there are these Takagi units that break locally the Ice rules. Now, the classical order disorder model could not explain the isotope effect, and so people used the quantum tunneling model, and the quantum tunneling model can be represented here by a variation of Ising in transverse field model. And so in this, according to this model, there is a soft mode instability and symmetrized hydrogen bond in the paraphase. Now, neutron diffraction ruled out, hydrogen bond symmetrization, and deep inelastic neutron scattering found evidence for proton tunneling in KDP, but not in DKDP. So that's what happens here is that if we consider this is the hydrogen between two oxygen that bind the two phosphate group, and in this XY plane, we can define the displacement of the proton with respect to the symmetric position in the middle. And I call it delta XY. This delta XY, when we are below the transition temperature, there is broken symmetry, and so it is on one side, but the displacement does not change much if we go from below the transition temperature to above the transition temperature. So that is also known from experiment. So now we did, in this case, we can use the methodology, but we have to use path integral molecular dynamics simulation in order to include quantum effects and in the nuclear motion. And so again, we adopt this methodology, and we went up to this number of units and up to 128 beads for the ring polymer. And we could do trajectories longer than nanoseconds, several nanoseconds for statistical sampling. Now, again, here we face a basic difficulty with DFT. DFT underestimate the tunneling barrier, even though at zero temperature, the DFT predicts the correct structure, ferroelectric structure. As soon as we switch on the quantum zero-point motion, what happens is that the system becomes paraelectric. And therefore, we had to reduce this effect. In order to reduce this effect, we stiffened the spring constant of the ring polymer to match the values delta that are extracted from diffraction experiment. So again, it is an empirical fix, but this empirical fix is sufficient to bring the picture in close agreement with experiment. When we do that, so it's like increasing artificially the mass of the proton and the deuteron. All the rest we leave unchanged. And so when we do that, what do we get? We get, for the polarization, we get this behavior. Again, it is the transition is smoother in the simulation because of finite size effect. And but we can reproduce very well the difference in polarization between the KDP and DKDP, and the temperature that we estimate from this drop in the polarization are close to the experimental transition temperature. And also the structural distortion is slightly underestimated, but overall predicted correctly. We can see here that it doesn't go immediately to one, it goes continuously because, again, of finite size effect on this simulation. This is, yeah, if you want, there is imaginary time. These are path integral in imaginary time, yes. Yeah. And now, what is the origin of the isotope effect? Well, we can, since we know all the configuration, we can project all the configuration on the these phosphate units that were originally introduced by Slater and then by Takagi. And we find that these units that have an even larger violation of ice rules never happen, but these units happen. And what happens is that these Takagi units that give rise to local fluctuation of the charge, of the nominal charge of the defect, actually are dominant at low temperature in KDP, even though energetically, from a classical point of view, this unit will have low in energy, but that is due to the fact that a bond switch due to the to tunneling actually create this kind of defect. So the difference between DKDP and KDP is due to the different role of defects. We could go up to 50 Kelvin, but we extrapolate, simple extrapolation, we get a substantial fraction of these defects should be present also near zero temperature. Now, so there is always quantum disorder induced by quantum fluctuation in KDP. This quantum disorder confer residual entropy to ferroelectric KDP. which is consistent with the smaller transition entropy delta S relative to dkdp. Also, at very low temperature may contribute a specific heat linear with T in excess of the Debye law. And indeed, this has been found experimentally. According to our model here, there should be an intrinsic, could be an intrinsic effect in the system, but in the experiment they found dependence on the sample preparation. So it is difficult to distinguish between quenched and intrinsic disorder, but certain, yeah. Well, well, there is disorder that is due to the quantum fluctuations in this case, but this quantum fluctuation. Well, I mean, it cannot be intrinsic, like pure systems. Well, we could not go to this. We should go at around at 1 Kelvin or so. That is impossible in the calculation at the moment. So the only thing that I'm saying is that there are two-level system, because these hydrogen bond switches will be present at near zero temperature. And so when we found that from the simulation, I said, well, let's look at what experiment found for the specific heat. And indeed, the experiment found for the specific heat, there is a linear contribution to the specific heat. So this is just a guess from the calculation, but is not really supported by the calculation, because we could not compute the specific heat at low temperature. So then let me just move to the last example. So the last example is also a system that has been studied quite a lot. And this is relaxor ferroelectric. In this case, we consider PMN. That is a perovskite structure, but there is chemical disorder due to the fact that this B site is occupied on average by 1/3 magnesium and 2/3 niobium. And because of the chemical disorder, there is glassy behavior in the dielectric response function. This is taken from experiment. This is if we do the cooling in experiment. So at high temperature, the system is in thermal equilibrium, but if the temperature is lower, the system goes out of equilibrium. And that can be seen in the response function, in the fact that this is field cool, in which there is a field that is poling the polarization, going down and then going up. And one can see that there is an hysteresis associated with that, and that is in zero field cooling. Again, there is the fact that the zero field cooling and this other way of cooling gives a different result, is an indication that the system is out of equilibrium. And we can also see that in the real and imaginary part of the dielectric susceptibility. So we see that this peak in the dielectric, this is the real part of the dielectric susceptibility, moves as we increase. This is as a function of the frequency of the applied field. These are quite low frequencies, but as the frequency goes to zero, we get something that looks like that. And as we increase the frequency in experiment, they go up to 1 gigahertz. In this case, we see that this position, the temperature at which this peak move changes with the frequency of the field. And similarly, we have an opposite change in the imaginary part of the susceptibility. And if we associate a relaxation time to this variation of the peak with frequency, we get approximately in experiment, we get this Vogel-Furker law, which is also observed in magnetic spin glasses. And it is also observed in the response, in this case is the viscosity, not the dielectric susceptibility of fragile glasses, again, has this behavior. So there is some universal effect due to disorder in all these systems that are quite different. Now, just let me go quickly here, more quickly here. So in this case, we have to construct a model of the quench disorder in this system. And to construct this model of the quench disorder, we are guided by experiment that indicate that the disorder is inhomogeneous, that there are, on the scale of 1-2 nanometer, there are chemically ordered region and chemically disordered region. And so we have building blocks like that of about 360 atoms, in which we have the chemically ordered region in this case, and in this case we have a chemically disordered region. They both satisfy the stoichiometry of the system, and we can put at random this block in the simulation cell. They are like these bricks that are there in the simulation cell. So that's is an ad hoc model of the disorder, but is based on experimental observation. And what we see that when the system is cooled down, there is the formation of these so-called polar nanoregion, that are region in which the dipole moment tend to be aligned locally. Here we have a polar nanoregion, and they freeze as we go. At high temperature, the dipole fluctuate and the system is in thermal equilibrium, but as we go down, they freeze. And we can see also here by analyzing the distribution of the dipole moment associated the magnesium, niobium, and magnesium, niobium, we see that these regions are actually occur in niobium-rich region in the system, which is again in agreement with what is found in experiment. Now, well, this is an example. As we do the cooling, there is the formation of this region as we cool down. This is again is obtained from the molecular dynamics simulation. And since I mentioned at the beginning, we can study also the effect of an external applied electric field, and we get the polarization. We can study the static and also the dynamic response, real and imaginary part of the susceptibility. And we have to use frequencies that are higher than experiment because of the size of the simulation, but still we get qualitatively the effect that is observed in experiment. And here we have a difference between this static susceptibility, when the system gets out of equilibrium, the static susceptibility calculated from the fluctuation dissipation theorem, namely from the fluctuation of the polarization, or from the finite difference calculation, give different results, as was found already in some pioneering work in this field done by Belesh about 10 or so years ago. So, but here we get also this dynamic that also is in qualitative agreement with what is observed in experiment. I want just to say the last thing that we have studied. Now, we would like to understand more deeply what is going on there. And one thing that we did was to study the inherent structure. So the structure that can be quenched instantaneously from high temperature. We found that the rate of the quench was not important. We always get similar result. Once we have the inherent structure, we can then do the diagonalization of the Hessian that we know, because we know the potential of interaction between the atoms. And that is what we get. That is the density of state that we get. We could do that for similar model for PMN and for PTO. And this is the polarization associated to the different modes that are the eigenstates of the Hessian. And we can see that the polarization is present for all the modes over the entire spectrum, whereas in PTO is only present for some infrared active modes that are this mode over here. Otherwise, it is zero. And perhaps the most, this is a very quite interesting, and perhaps the most interesting thing is that we find out that this is the participation ratio associated with the mode. So the mode here at the onset of the spectrum at very low frequency are extremely localized. They have a very small participation ratio, and there are small participation ratio also here when there is a gap or things like that. But let's focus on this part over here. So we have this very localized mode, and we could study here with model with this number of atoms, we could study the density of states, and we get a clear indication that there is a contribution going like omega to the fourth power in the mode for omega going to zero, which is similar to what has been found for spin glass model, but also for structural glass models. And this is a universal feature because it doesn't depend on, well, we did it for a three-dimensional system, but it doesn't depend on the dimensionality like the omega square, that here is omega square. This is the Debye contribution that should go like d to the minus omega to d to the minus 1. So we have this universal feature of disorder. Is that related to the response of the system? That is a question mark, but definitely that is there, and it's there also in this other system. And it is quite interesting that we can do this kind of studies with a very realistic model. Obviously, there are also issues related to what kind of localization one has for these modes. Is that Anderson localization or some other kind of localization? That in the structural glasses model, there is indication that the localization is not exponential, but has a polynomial dependence, but they could study system with up to 1 million atom and more with, and here we cannot describe that, but definitely this omega to the 4 is something that we get. So with that, I want to go to the conclusion. So deep potential molecular dynamics model are in surprisingly good agreement with experiment after empirical fixes and after designing a proper model for atomistic disorder. We got a better understanding of order disorder versus soft mode features in PTO. We identified defect responsible for large isotope effect in KDP, and we provided further evidence in support of the dipole glass model for PMN, which would be a sort of spin glass. We also studied the Edwards-Anderson order parameter, and we find the correspondence of that with what one obtained with the spin glass Hamiltonian that include also random fields that are present in this system. So that's it, and I thank you for the attention. We went from 2 gigahertz, so the highest experimental was 1 gigahertz. We went from 2 gigahertz to 100 gigahertz. 100 gigahertz. It's
you would expect linear temperature, but heat and a constant density of phase. I'm not sure whether your energy scale is low enough.
Well, this on the scale, if we go on the scale of, let's see, over here, we are still in this range here. Yeah, this is 10 centimeter inverse. I don't have a magnification of that, but we are still in this region here in which there is a strong localization. Of course, there is a different hybridization also of this mode with the phonon modes that are present, but
there is no glass node which the observer used the pole without observing a linear capacity.
Okay, but the heat capacity we didn't study. Yeah. 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 Yeah, yeah. Yeah, yeah. So the heat capacity we didn't study in the system, and also the heat capacity in the KDP model is difficult to study. We could do it in the PTO, but in KDP it's difficult to study because the estimator for the heat capacity when we use the path integral formulation has a lot of noise, and so we couldn't get the result for that so far.
Yeah. So I was wondering about the long-range dipole-dipole interaction.
Yes.
These are known to be quite important in the physics of ferroelectric perovskite. Like you have a giant alloy splitting and stuff like that. So is your deep potential model captured? Is accurate?
Well, that is not important in this ferroelectric, as in the, if you go in the how to say, in the PTO, in the case of experiment, the longitudinal transverse splitting that is associated to the long range is quite small compared to the effect, so does not explain the peak in the susceptibility. So it is a small contribution. We don't have it in this simulation, but in principle it could be included because we have a deep potential model that include long-range dipole-dipole interactions, again at a level of perturbatively by assuming that the effect of the long range up to dipole correction. And that we have not used in this model, but we have used that in model of other system. For instance, if you do want to study, we find it particularly important when we have to do really a liquid electrolyte in contact with an interface. The interface gets charged. If we don't have this long range interaction, we break charge neutrality in the bulk of the solution, and this is cured by this effect. This effect, we have also used this, studied this effect in calculating the static dielectric constant, for instance, of liquid water. The static dielectric constant of liquid water, you get a result that is independent on the boundary condition that you have only if you include the dipole-dipole, the long-range dipole-dipole interaction that gives a contribution that decays like 1 over the volume. Instead, if we use the model without this effect, we get an exponential decay, which is wrong. However, the difference between the two in that case is not so large because it is dominated by the clustering of this dipole at shorter range, and the difference between the two is actually smaller than the error of the DFT in the dielectric constant itself.
Well, yeah, may I ask another question?
Yeah, sure.
I see you use a maximally localized Wannier function to describe the local polar environment.
Yes.
But is it how physical is that? Because the Wannier functions are not really physical objects. There are several ambiguities in their construction. What spread function use, how you partition the Wannier centers between different cells or different atoms. So how do you make sure that this is actually...
Well, I think that the center of this Wannier function is the only information that we use here. The spread is not used in this calculation, only the center, because that is what is needed to define the dipole. And I expect that the center, these are all relatively large gap insulators, so it's more, it is easier to define this Wannier function in this system. I expect, but we didn't study the dependence on different localization criteria for that, but I would expect that the center will probably be always more or less in a similar position. Of course, there will be a dependence on the functional, but one can rigorously connect the definition of the polarization that I have there with the Berry phase theory of polarization. So that's that's it.
The total sum of the center.
This is well defined. The local.
Going to local.
The local is not let's say so well defined, but I think it does give you an additional interpretive tool, because you can see if there are correlation between these local dipoles or not, and lo and behold, this correlation, long-range correlation, disappear precisely at the transition temperature that has been calculated without using the dipoles, because we did also a free energy analysis of the transition temperature. Yeah, yeah.
Are there questions online? Tamika, we can't see the name, so if you see hands raised, just shout out or unmute them. While we wait. What is it for the first step to get the,
Yeah, yeah.
how is it effective? So what is the input? What is the output? What is
The coarse graining, I didn't spend time in describing that, but since this is based on DFT, you get the potential energy for a given configuration, but you also have the electronic Kohn-Sham orbitals, and from this orbital, you can construct the Vanier functions. But let's say just for the potential, we have the energy for a given configuration, the potential energy. This configuration need not be just a configuration at zero temperature, but is a configuration that is sampled during along molecular dynamics trajectories. So we have a technique of active learning that basically it is based on what I can call an on-the-fly version of the what is that called, training by committee or consensus by committee. So we have an ensemble of neural network models that are characterized, that are constructed based on the same configuration, but use different random initial condition for the hyperparameter that then are obtained by using stochastic gradient minimization. So we get, presumably with this procedure, we get to different local minima of this complex potential energy landscape. But when a neural network is well trained, all these different local minima give rise to similar physical prediction. So we consider the spread in the prediction of these different models that are trained in this way as an indicator for when we have to acquire new quantum mechanical data. So we have to minimize the number of quantum mechanical calculations, because even though DFT is not as expensive as quantum Monte Carlo, is still quite expensive when we have to sample, let's say, tens of thousands of configurations. So we only, so we do the sampling with a deep potential model that is refined iteratively. As we go for these different configuration, when we find that the spread in the prediction for the forces exceed a certain threshold, then it means there we need to acquire new quantum mechanical data. And we keep going like that for several cycles until we end up with a model that describes with uniform accuracy the phase space in the region of interest.